Hi, my name is Marn Schokker and welcome to this beginner workshop about displacement techniques in Houdini. This video is part of SideFX's Project Grot, where we were challenged to build a lava cave environment with the help of procedural workflows. We needed a quick way to generate unique, complex and interesting rock geometry for our environment, so we knew that a user-friendly Houdini tool would be the best way to quickly iterate on the scene. Additional material and source files will be shared at a later date and linked below when available. Here we can see an example of the tool being demonstrated in Engine. With the preview mode, we can quickly make variations on the base shape by defining where detail will be placed. With the version shown here, there are options to configure two separate displacement textures based on the black and white areas of the blockout. Each can have a different scale and strength. Here you can see how the settings can be changed to create a different look. Now that we have seen what you can do with procedural displacement in Houdini, let's go over what we'll cover in this workshop. At any point, feel free to jump around using the chapter navigation or timestamps in the description below, where you'll also find links to useful and appropriate documentation. We are going to start off with a bit of Houdini configuration to make sure that SideFX Labs is installed and that the desktop is configured to our liking. We will then properly kick off with an introduction to displacement and look at various techniques in Houdini. At the end, we will create a simple rock tool of our own. Before getting started, we're going to set up Houdini so everyone is on the same page. Feel free to skip this section if you've already got SideFX Labs installed and your Houdini layout configured to your liking. To follow along, I'm using Houdini version 20.0.590, but don't worry if you don't have this exact version. Any recent version should do the trick. You will, however, need to have SideFX Labs installed. I've linked the documentation down below, but here are the simple steps. When you launch Houdini, you can check if you've got Labs installed by checking the SideFX Labs shelf at the top. If you don't see it, press the plus button, hover over Shelves, and tick the SideFX Labs menu entry. Press the Update Toolset button. If it is not installed, press the Start Launcher button and wait for the launcher to pop up. Then select Labs/Packages and Install Packages. A menu will pop up, which can take a minute or so to show you the installation options. Once this is installed, reboot Houdini for the installation to take effect. By default, Houdini will launch in the Build desktop. You can change your desktop here at the top. For this tutorial, I'll be changing the layout a little bit. I will close the tabs above the network view and split the viewport pane vertically by pressing the arrow in the top right. We will then turn the bottom pane into a geometry spreadsheet, like so. We can also collapse the shelves. To save your layout, press the Desktop drop-down and press Save Current Desktop As. To make Houdini always launch with this configuration, open the General User Interface Preferences under the Edit menu and set the startup in Desktop entry to the one you saved. Now that everything is set up, let's talk about displacement. The concept, as you can see, is quite simple. You take a point and you move it. There are two main types that we'll talk about, namely world space and local space displacement. With world space displacement, you directly apply a three-dimensional noise on the position of the point, while with local space displacement, you use a point's normal direction and move the position along it using some input data. This is all still quite abstract, so let's go over a couple of different techniques in practice, from easiest to most difficult to implement. With Houdini just opened, we will start by creating a geocontainer that will hold all of our work. Just press Tab in the network view and type geo, followed by Enter to place it. double click on it, or press enter again to go inside. For our examples, we will use a simple box. In order to get any resolution out of our displacement, we will increase the axis divisions to a value of 40. If you don't have a parameter window in your desktop layout, press P to bring up a floating window. If you hold middle mouse button on the axis divisions label, you can increase the values for all of these at the same time. One easy way of applying some world space displacement is using an attribute noise node. There's a useful preset that you can find that applies to position by typing mountain in the tab menu. Connect it to the box and you can immediately see a result. Feel free to play around with the values to tweak the output. Another Houdini context that I want to introduce you to is called VOPs, or Vex operators. This won't make a big difference for this example, but we can easily adapt this to apply local displacement later on. We can connect a point VOP to the box and double click on it to go inside. This will look a little different from the regular network view, and it appears to be more similar to a material graph that you might be used to from a game engine. When you press tab, you will see a completely different list of available nodes. The one that we will use for now is called anti-alias noise. Once we plug in the position, we won't see anything happen. That's because it generates a new offset that can be added to the original position. Place an add node and connect both the original position and the output from the noise node to it. As you can see, it looks like the noise is skewed. This is because the noise node is set to output a one-dimensional value that is being interpreted as a three-dimensional one when it's added to the original position. When we set it to a 3D noise signature, we get the expected outcome. In the same parameters window, we can change the appearance of the noise as needed. The next level of displacement we will talk about is triplanar displacement. This is a sort of hybrid between local and world space displacement, where the points themselves are moved in the local direction of the normal, but the amount that the points are moved in is computed in world space. Despite the difficult description, this is actually really simple to implement, so let's have a look. Before we start, we do need a texture to displace with. The one that I'll be using for these examples can be downloaded on sidefx.com as part of the content library, linked below. This rocks pack will be downloaded as a zip, but the only file that we're interested in, for these demonstrations at least, is the rocks_height.rat file. Extract this somewhere where you can find it easily. Back in Houdini, we will now connect a triplanar displace node with our box. If you don't have SideFX Labs installed, this node will not be available to you, so make sure you follow the steps from earlier in the video. We can immediately see that it applies displacement to our mesh based on an included UV test texture. In the parameters, we can specify the texture that we have just downloaded. The last type of displacement I would like to touch on as part of this introduction is UV-based displacement. Before we get going in Houdini, I want to quickly recap and discuss what we need. Just like any other displacement, we will need a lot of points for a high quality result. And just like triplanar displacement, we will need some sort of normal information and a texture. But what we will also need is UVs to apply them. This workflow works well in geometry that it can be UV'd nicely, and can work around some of the axis blending issues of triplanar mapping. The easiest way we can add UVs to our box in Houdini is by just using the UV unwrap node. The default settings will work just fine for us. We will also need to sample the displacement amount from a texture based on these UVs. For this, we will add the attribute from map node. Just like with the triplanar displace node, we will need to specify the texture map we have downloaded. Depending on your UV scaling, you may need to set the wrap mode on the filter settings to repeat. We can either plug this into a new point fob or our existing setup, but the only thing that we'll need inside of the point fob is a displays along normal node. Connect the P and N inputs and outputs appropriately and plug CD into the amount. In the parameters of the displays along normal node, you can change the amount of displacement using the scale parameter. If you want the texture to tile less or more, just scale your UVs. For this part of the workshop, we'll jump over to a live demonstration of how to create a rock displacement tool. So first of all, let's start off with the subnetwork. This will make it easier for this to be turned into an HDA at some point. As you can see, we've got 4 different inputs on our subnet by default, and we will want to provide our tool with an input. So let's just make it easy for ourselves and start off with the tube. Just add it there, and if we set our view flag on it with the blue and purple icons, we can just change these settings a little bit to make it more interesting. So I'm going to add end caps, and I'm also going to change the radius of the top part a little bit. There we go. And I'm going to plug that into the first input. Double click on the subnet to go inside, and this is where we'll actually get to create the tool. So I'm going to create a little bit of space for myself, and I am going to disconnect the output from the input. If I hold Y, I can start cutting. These I'm just going to put aside, and if you hold A while dragging on one of these with the left mouse button, you can align them just to make it a little bit neater. And I'm also just going to add a null node to make it easy for me to see what is actually going on with the inputs. One problem with the input at the moment is that we don't have a lot of geometry. So a node that I like to use is called remesh to grid. One advantage of this one, because it uses VDBs under the hood, is that you can merge in multiple disconnected pieces in the inputs. So I'm just going to quickly duplicate the tube here. If you alt drag on a node, you can create a duplicate, drag that in, and this one I'm going to change slightly in position. So I'm going to put the center slightly to this side, like so. Merge them together, and now inside of the subnet, you see that they're all part of the same geometry now. One thing that currently is an issue with our mesh is that it's too simplistic, and if we're now going to add displacement on top of it, you will clearly still see that this is the underlying shape. So one thing that we can do to break up the base shape is by copying some meshes on top of the surface, for which we're going to use the copy to points node. So type copy to points, and as you can see, we've got 2 different inputs. We have the geometry that is actually going to be copied, and we need some target points. Just as a quick example, I'm going to connect this one to the target points, and I'm going to scatter a platonic solid. So type platonic solid, which we can then connect to the geometry to copy. If we now have a look at this node, we see kind of a crazy result, but that's expected, because on each of these points of the input mesh, we're now instancing or scattering one of these platonic solids. To control how many of these are placed, we can use a scatter node and plug that in between these two, which we can do by holding this connection and dragging it over to the scatter node to connect it. And as you can see, the scatter node adds a bunch of points on top of your input geometry. I'm going to disable force total count and instead use the density scale slider. I think a density of 10 actually works quite well for this input geometry. But if we have a look over to our copy to points node, there currently is an issue where the platonic solid is too big. So let's actually make it a little bit smaller. There's a radius slider that we can drag. And I'm also going to change the solid type. Currently it's a tetrahedron, but I'm going to change it to icosahedron instead. And to also make it more obvious what the direction is of each of these individual shapes, I'm going to non-uniformly transform it. So I'm going to stretch it in one particular direction. Unfortunately, we don't have any options on the platonic solid node itself to do that. So we're going to add a transform node. And again, just left mouse button drag this connection on top of the transform node to connect it. Inside of the parameters window of the transform node, I'm going to change one of these scale settings, for example, the Y component of scale, by holding middle mouse button on it and just dragging it to the right. So it's now stretched in one direction. And now if I have a look at the copy to points node, you can see they are indeed stretched. I might just make it a little bit smaller again. So now that we have these individually copied pieces of geometry, we would like to merge this back with our input geometry. So for that we can use a merge node. So again, we can type merge, drag this one in, and drag this null node in, which we should probably rename to something like input underscore geometry. Then I'm going to connect this one straight to the merge node. Another issue that we're seeing right now is that it is too uniformly scattered. So there's a really useful node that we can add. It's called labs random selection. So again, for this you will need to have labs installed. And we can drag this one in between the scatter node and copy to points. It won't do anything just yet, but we can set our view flag to this node and activate our parameters window by pressing P again. So there's this ratio slider, which we can use to randomly delete some points. I can use the delete selected option to select a ratio of the total number of points that will be deleted. So now if we have a look at our merged result, we can see that a little bit of the mesh is now peeking through again. Another thing that we can do to prevent these meshes from sticking out too much is by making sure that we provide some orientation attributes to this copy to points node. So I have demonstrated a little example here, and copy to points specifically looks for certain names that it uses to base its orientation off of, and we're using N and up as a workflow because it's easier to understand and visualize. Now if I have a look at this copy to points node, I'm going to press H in the viewport to center our view. We can see that we indeed have a random orientation. And if I were to disable these two nodes by hovering over one of the nodes with them both being selected and pressing the bypass button, you can see that by default it just points up. So we're going to use these two attributes to also drive the orientation of the scattered meshes on top of our base mesh. So the first thing that we can do is adding a normal node right before scatter, and you'll see an immediate result. They don't appear to be following the direction of the mesh, but they are at least not sticking out. So what we can see now on this scatter node, if we enable display normals, is that we do in fact now have normals on these points. These are transferred from the original geometry to the points. And if you press the I button, you can see it is a points attribute. As I showed in the previous example, we don't just need n for deterministic orientation for copy to points. We also need an up attribute or an up vector. And to generate that, I've come up with quite a unique method, which I will demonstrate shortly. So one thing that we can do is generate flow curves from the bottom of the mesh to the top and use that direction as the up vector for our copy to points operation. The node that we'll be focusing on to achieve that is called find shortest paths, which you can find by typing find shortest path. And if we just drag this in, nothing will happen just yet. It will actually give us a warning. The warning is no start points specified. And it also actually expects endpoints as well. So what we want, if we look at our original mesh here, is to select a number of points as start points at the bottom and also a number at the top. What I find the easiest way to achieve this is to sort the points of our geometry in Y. So for that we can use the sort node. If you press P again to bring up the floating parameter window, we can set the point sort to Y, which we can visualize in the viewport by pressing the display point numbers button. So now we can start to think about generating a group based on something like the bottom 5% and maybe the top 5% of point numbers. So there's another really useful node that we can use for that. It's called group by range. Find shortest paths expects a point group. So let's change our group to points. And now we can play around with these sliders. These channels support expressions, which we'll make good use of now. The one that we're going to use is called endpoints, or number of points. Because this is a function, if we start typing the first opening bracket, we'll see the definition of the function. It expects a surface node. This is just a reference to the geometry that we're using. And if we type 0, it will give us the number of points of the first input of this node. So if we hit enter, if you left click on it, we get the total number of points. If we type divide by 10, we'll get the bottom 90%, but if we click on invert range, we'll get the top 10%. This is going to be our end group for the find shortest path operation. So we're going to name this one end PTS. And we're going to add another group by range node by holding Alt and left mouse button dragging from the group by range node and make sure that it is connected with the last output from group by range. To select the bottom 10% instead of the top 10%, I'm going to copy this by clicking on it, then Control A, Control C, and pasting it in the start field. Hit enter. And now we're going to want to clear out this end parameter, which you can do by holding Control and Shift and left mouse button clicking on the label. Now it says 57 instead of the expression, which we can replace with 0 instead. And if we just change our view, we can indeed see that the bottom 10% of points are selected. Another thing that we can do to reduce the amount of points that we're going to use for find shortest path is using this range filter. Otherwise, we're going to have a lot of start points and a lot of endpoints that it will connect, which will result in a lot of geometry that we don't need. So I'm going to set this to something like 5 or 7 even. And I'm going to do the same with the endpoints. Now we're ready to plug this into the find shortest paths node and set up our start and endpoint groups. Type start PTS for the start points and end PTS for the endpoints, and we can see some of these connections forming, although not all of our start and endpoints got connected. So what I like to do is changing this output paths option to each start to each end. Disable the point numbers so we can see this a bit better in the viewport. This now generates a bunch of individual curves that we can use to derive the direction from. For that, we're going to use the orient along curves node, which you can find by either typing orient along curves or just the first 3 letters of each individual part of the phrase. So that is OAC, one of my favorite features of Houdini. Connect that with the previous node. We already used the n attribute from the original geometry, so we're interested in setting the up value instead. So we're going to set the tangent to up and just clear out this one. We can visualize this attribute by pressing the I button and pressing up. And as you can see, this is our up vector. And now we're going to want to find a way to transfer this data to our random selected points that are used for copy to points. Currently there are 2 connected streams of geometry. So there's a very useful node that we can add. It's called attribute transfer. On the left is the geometry that will receive the value, and on the right we can plug in the geometry to transfer the attributes from. So as you can see on these points, the visualization of the up attribute still works. If your visualization does not work, you can press this visualization icon in the viewport. If you right click on it, you can even disable or enable individual visualizations per attribute. Now that we have this attribute, we can plug it in to the copy to points node on the second input, and we can have a look at our copy geometry. We can enable and disable the attribute transfer to have a look at the results. Now if we have another look at our merged together geometry, there's one more step that we need to do before we can start applying displacement, which is connecting it into one piece of geometry. This is similar to what we did at the start of the graph. So we can just actually copy this remesh grid node, paste it here at the end, connect the output of the merge node with the remesh to grid node, and we will also need to increase our resolution a little bit for displacement, because as we've covered previously, we need a lot of geometry for a high quality result. So I'm going to set it to a value of 0.01. Depending on the size of your input geometry, you might need to increase or decrease this division value. So we're going to add a triplanar displacement node, labs triplanar displace, and add it after the remesh to grid node. By default, it's going to use the UV grid again. So I'm going to change it to a texture that I've downloaded from the content examples. You can see an immediate effect when changing the values of the triplanar displacement parameters. I'm going to try and find a value that I find appropriate for this mesh. This looks good to me, although there are a couple of issues here that we can work around. The easiest method is just adding another remesh to grid node right after, at the cost of performance. This will smooth out these sorts of issues. There's another thing that we can do, which is using curvature to drive the displacement scale attribute here in the triplanar displace node. We're going to add a measure node right before the triplanar displace. Set it to curvature on points. We can visualize this again in the viewport by pressing the I button and pressing curvature. We can already use this inside of the Triplanar Displace node by connecting it and enabling the option Use Displacement Scale Attribute. By default, it's looking for one called Displace Scale, but we can change it to curvature now. And if we view this node, we can see that it only applies displacement to the edges, but it is actually the opposite that we want. So we can press this button, Invert Attribute. I'm going to disable this visualization, and this should have already helped with a couple of these issues that we saw, without us having to use the Remesh to Grid node again, which can be computationally heavy. There are some jagged edges which we can work around by adding an attribute blur node. So I'm going to add that by typing A blur, press enter, drag that in between. And we will not want to blur the position attribute, but we want to blur the curvature attribute. So if we just type curvature instead, as you can see, that issue is now also resolved. There are two more things that I want to do to make this result a little bit more pleasing to the eye. One of them is adding some random sizing to these copied pieces of geometry, which we can do with an attribute noise node. Drag that in between the attribute transfer and copy to points. Instead of randomizing the color, we're going to randomize the scale. The easiest way of doing this is by typing B scale for point scale. This should be a float. We can use this option, enable remap ramp, to define our desired values. I'm going to make them a little bit bigger and organize my graph a little bit again. The last thing that I want to do is to add a little bit of variation in the amount of displacement. So currently we already use this curvature attribute, but we can also randomize this a little bit. I'm going to add an attribute noise node to add some variation to our triplanar displacement. Drag it in between the attribute blur and triplanar displace. Set the attribute name to curvature, as that is what we are already currently using, and change the attribute name type to a float. If I now view the result of this attribute noise node, we can see that it has an immediate result. I want to change the element size so we can see the noise a little bit clearer. Now we can have a look at the triplanar displace node, disable the visualization and see the result, and compare the added detail by enabling and disabling the attribute noise node. In my opinion, it makes it look a little bit more natural. If you want the result to be less obvious, play around with the amplitude setting. Now that we're done with the simple tool, we can connect the triplanar displace node to the output and go up one level and compare how our input looks with the outputs. To close off this presentation, I want to show you a quick breakdown of the tool used in the project. You will recognize a lot of the techniques that we've discussed today. I start with the simple input mesh that has been merged together using a Remesh to Grid node. I then generate some automatic UVs. These are later used for a bit of extra UV-based displacement, but they are also very useful when exported to the game engine. I get start and endpoints based on a relative Y position and use these to find the shortest paths to the top. Orient along curves is used to get the direction, which is subsequently transferred to scattered points on the geometry for use with copy to points. This is merged together with the UV'd base shape. Displacement is applied on relatively flat areas of the mesh in two passes. One on the platonic shapes from copy to points, and one on the remaining geometry. This allows the user to specify two different displacement textures. At the end, I export some additional data in vertex color, which can then be used in Engine for the material. Thank you very much for watching my workshop. My name is Marn Schokker, and I hope you learned something.